Howdy, everybody. Hope you're doing well, wherever, whenever you are. I truly mean that. I hope all's going well with you. We had another relatively easy day. I think probably, I was going to show you, I'll show you in a minute, but probably because I happen to have solved a Caddis problem that had a similar stuff, and we've done stuff like this before, so it wasn't too bad. Anyway, not too bad of a day, so I thought I'd post it right now just so everyone could see what my solution is. I love the comments and the interactions, especially on Reddit, so it's really cool. I feel like I'm growing and learning things from everyone. I had some time during a boring meeting at work to optimize the previous day, so you'll see that in the recap. Otherwise, let's get cracking. So this was day 13, unlocking the mountain. And if you remember last time, we blew up a bunch of barrels. The whole castle's in disarray. And you notice that there's, you go to the mountainside where they're being held in the cave. And there's a lock there that you have to unlock. And the guy who was guarding it ran away but left the directions. You scared him away. So anyway, I thought it was a pretty fun day. It's like, can you unpick the lock? And like I said, I did this Caddis right here called combination lock, where you do a similar thing. It's not quite the same, but the idea is like, can you figure out how to turn the dial and stuff like that? And so if you've already done that before, you already know how to like turn the dial. It's pretty easy. Again, they're just modulus operations, so they aren't that too difficult. But like almost anything, if you haven't done it before, maybe it takes a little bit of time to think about it until you come up with a simpler solution or understand it enough that you can code it efficiently, maybe is the way to say it. So that's what happened. So for part one, what does it say? It says you're given your notes and it's just a list of numbers, but it says like the way that you place the numbers is like you start with the number 1 and then you place the first number to the right and then the second number to the left and then the next number to the right and then the next to the left and back and forth and so on until you've gone through all the numbers. So the idea is you're going to do this. You're going to take these numbers and put them on the back or front of the one, or maybe of the array, the list of items you have. You start with just one, the number 1, and then you put one there, all the way until you put them all. And they give you a pretty good example. Like you start with a 1, then you put the 72 over here, then you put the 58 on the other side, 47 on the other, 61 on the other, and then 67 down at the bottom. So now as you like turn the dial, you can see you'll hit 72, 47, 67, 61, 58, and then come back to the 1. And what it asks you is like, once you've put it together, what happens when you spin it 2025 times? And I think like I mentioned before, this is just like a combination lock. So the gist of it is once you've figured it out, once you've created the wheel, I guess is the way to say it right here. Once you've created that wheel, you can simply just say, oh, well, go to the 2025th position, but do it modulus the wheel lane, and that will get you to the right position. So it was just a question of like, how do you insert them? And the way that I came up with really quickly, I had 2 thoughts, and I think you can do them both ways. One was to use like a vec deck. So you could efficiently like put one on the front and then put one on the back, and then on the front, then the back, then the front, then the back, then the front. And then once you've got it, you can use like a shift left, I would think, to like shift all the things on the front to the end. So you start at number 1. The alternative is if you've like built it that way, you just need to do 2025 plus the wheel length divided by 2. These are all weird ways of saying you just really need to build the lock and figure out how to do it. The way that I chose to do it that I thought was kind of cool is I said, oh, I can actually do an iterator. I think we've done this before, is like if you want to like take every other one, you can do a skip step by 2 and then to get the odds, and then you can do a skip step by 2 to get the evens. In the left side, we want to get them in reverse though, right? So we want to get all the odd values, but we want to get them reversed. So that's why we call a reverse. And we do the copied here so we can get actual values, like in U sizes, I guess is the way to say it. So I mean, it might be even more efficient not to copy. I don't know. U sizes are small enough that you may not be worth copying. So anyway, that was it for part 1, is like, how do you do that? So once I have my iterator, I can just chain. I start at the middle, which is the 1, and then I chain the right hand side, and then I chain the left hand side, and that will give me the wheel in order. That was it for part 1. It wasn't too bad. So you can see that I got the answer. I think I got the answer wrong once, and it was because I had chained them the wrong way. I think I had done left, middle, right, but because the left side is like should be at the end, so it's middle, right, left, if that makes sense. But anyway, it wasn't too bad of a day. So how does part 2 change? Well, they say you don't just get numbers anymore, you're going to get a range of numbers. So you're going to get one end and then another end, and then you're going to spin, or you're going to explode that into your list, right? So from 5 to 19 means you want to place 5 to 19 on that side. So you're doing the same logic. Like if you're using iterators, you're still going to have a left and right side, but now you're going to add the numbers 5 through 19 as opposed to just a single number. And you're always going to be given ranges. I think I've cleaned it up since, but in my original solution, I checked for both and returned them. And so that did make it a little bit more complex, but not much. However, the way that I fixed that was I just did a check that said if it doesn't contain a dash to like create a dash to like string them to get to. So like if it was just a 1, I would just do 1-1, and then that would have the effect of doing that, right? Excuse me. Okay, so what do? You're going to do the same thing. You're just going to do it with the ranges, and it shows you how to do it, right? So if you get the numbers 10 through 15, you go 10 to 15 on this side, and then the next one is like 12 through 13, so you'd put 12 here and 13 here. And that was a gotcha for me. I was like, oh, the first time I did it, I got the wrong answer, and it was because the numbers are actually reversed. So you actually have to track where they're back. The ones that are put on the left side are actually backwards. They're reversed. So you're going to put the numbers separately. And you'll see I added a thing to do that. I kind of, and maybe this is what made part 3 super simple, is doing this. I was like, oh, what if the numbers are like extremely large? And some of these were, 3,000. This was 4,000. And so I said to myself, is there a more efficient way of like doing this? Like maybe I can just track the 2 values and then do some subtraction. Because like in my mind, I was saying part 3 is probably going to give you some absurd values. And in fact, it does, right? Look, there's like absurdly large values. So how do I implement that? Well, I just keep track of both pairs, right? Both sides of the range, and whether it's on the back side or the front side, like whether it needs to be reversed or not is the way to think about it. Like this side needs to be reversed, these sides don't. Or like this side is backwards, these sides are not backwards. And then I can just tell how far I'm going to turn it by the difference of these 2 numbers, right? So I know if I'm in this range, I'm going to go 5 numbers, and it's actually 5 plus 1. I had an off by 1 error, right? Like if you're at position 10 and you want to go to you'll go to the next one, it'll be plus 1, right? So anyway, I'll show you that in a second. I had an off by 1 error. But once I do that, then I can just like go through the wheel pretty efficiently, right? And I don't have to like build out the huge vector of values because I've figured that out. But hopefully you understand the problem for part 2 is basically the only thing that's changed is you're exploding these numbers into the thing. And I think for part 2, you probably could have actually just put all the numbers on the list. But part 3, you wouldn't have been able to. I don't suspect because the numbers looked large. So how does that change? Well, I have a different input parser for part 2 and part 3. We're going to track the ranges, right? So you can see as opposed to just returning the value, I call split once and then return the 2 values. So the left side and the right side. And then I made a make wheel function and a spin wheel so that the parts themselves, part 2 and 3, are literally just say make a wheel and then spin the wheel this many times. So what does the make wheel do? It's the same thing. We just want to track if it's backwards or not, right? So as opposed to sending a range, I'm going to or instead of doing a single value, I guess for part 1, I'm going to have the range and then whether the values should be reversed or not. So the left side is going to be, yes, we're going to return we're going to want to switch the values. The right side and the 1 is not, right? We're not going to have to change those. So those are both false. They'll stay true to their like values. So that's how you make the wheel. It's the same thing as part 1. You just have ranges now. You still start at the middle, chain the right side, chain the left side, and collect them into your vector. So then the last part is just spinning the wheel, right? So given some wheel, how many times do you want to like move the ticks? I think the reason I used ticks again was because, oops, what am I doing here? Oh, I don't have that anymore. This maybe. I think in here in this combination one, I'd done this one before. I think when I was solving this one, or maybe it says it in here somewhere, it talks about the number of ticks, right? Anyway, so that's why I use ticks. So just think about a tick as moving from one position to the next. How many like do you want to do? There might be a better way to do this, but I just kept track of like the current position in the lock. So this I is like where I am at the lock. These are probably named poorly and we could name them better. But the idea is you just say, I'm going to start at the 0th position on the lock and then increment that every time I go through this loop. And what do? I just get that ith position. Again, I'm using modulus the wheel lane. So I get that ith position, and that will give me my left side, my right side, and whether it should be backwards. I know my diff is R minus L. And so I just do a check. I say, hey, if the number of ticks left is less than or equal to the diff, I know I'm in this block. So I just return, if I'm backwards, it's R minus ticks. Because remember, if you're going backwards, you're going to start at the end and you're going to go backwards that many ticks that are left. So if it was like, say it was 19 to 23 and you needed to go 2 more ticks, right? If you're going forwards, it's just you're at 19 and you go 2 forward, so it's 21. But if you're going backwards and it's 23, you go back 2, so from 23 to 22 to 21, because it's reversed, right? So you just have to remember that it's reversed. So again, if it's backwards, you do the right side minus the ticks. If you're not backwards, it's just L plus the ticks, right? So that's the difference. So again, this is if you finally reach the spot where you're going to finish the number of in the range. Otherwise, you take the ticks and you subtract it from the difference, right? So you say You say tix equals tix minus diff plus 1. I had an off by 1 error that was like briefly screwed me up when I was doing the test input right here for P2. It was saying, oh, the number should be 30, but you were getting 33, and it was an off by 1 error, right? So if you think about it, you're always going to tick at least once. And so it's going to be the difference of the number of ticks of the values plus 1 to move you past it. But anyway, otherwise you increment I so that the next time when you come around, you're getting the new wheel value. And that was it. That was part 2, right? So again, for part 2, you're going to use this bigger number, right? That's what they say. Use this bigger number to find it. So, you're going to go through the thing in a much larger set of numbers. But again, because I'm keeping track of the ranges, I can like do it wholesale in chunks, I guess is the way to think about it. And so how does part 3 change? Well, there's honestly not much to say about part 3. They just say, now you're given a bunch of bigger numbers and a whole lot more of them, right? You can see the ranges are like gigantic and there's a lot of them. Presumably you wouldn't be able to fit this all into memory. I don't know. Maybe you could. I actually don't know. I had already solved it the other way, so I literally just copy and pasted. I've since cleaned it up, but at the time I just copy and pasted and incremented this number, and it solved pretty fast. But yeah, that's it. That's all that changes in part 3 is it's a much bigger thing. And I suspect if you were literally expanding the ranges in part 2, you'd probably have to come up with some other solution, though I could be wrong. It would be interesting to know what the differences are. I guess I could do that really quick. We parse the input and we just say print line iter dots map LR R minus L dot sum U size. Apparently not. Oh. Uh, 100 million billion? No, 100,000. 274 million ints. We could ask Gemini or Google or something like that. Let's ask Claude. Should be fun and ask someone new. What is or how much memory would be required to store 274 million, even if we make it small U32s. That's a Vec. My guess is it's like you're into like the terabytes range, right? But I could be wrong. Gathering thoughts. I could do the math. Who knows if maybe I do have to. Yeah, one. Okay, so I mean, that's not impossible. Oh, I was thinking it'd be terabytes. So 1 gig, you could. Oh, do you know where it probably becomes inefficient? Is you're now creating. You're doing your pushes and pops. 274 million times, and so maybe that makes it inefficient as well. I don't know. Who knows? I actually didn't check my progress either. So anyway, all it is to say is I kind of suspected part 3 would be what part 3 was, especially because of like previous part 2s and 3s and stuff like that. Like I said, in Advent of Code and in Everybody Codes now, it's pretty clear that often that there's something that happens between the two parts that requires you to be more efficient. Sometimes guessing is not good because it turns out not to be at all the same, but in this case it turned out to be great for me. And I think both ways, it's probably the most efficient way to do it anyway, is to keep track of the ranges. We'll look and see. I haven't looked at the Reddit yet, but there's potentially more efficient solutions. So there you go. Let's just, in conclusion, look and see how my bird's growing. I actually hadn't looked at it yet. I actually don't think I've looked at it in a couple days. Oh yeah, we're getting bigger. Oh, we're buff. Oh, we got horns. We got horns. We're a dragon duck faux show. Looking good. Okay, let's check my times. Yeah, I think it went pretty good. What is this? 61st first placed? Is that what it says? So 61 solve. Yeah, again, going from again, you can see part 2 to 3, it was literally I copied and pasted and then changed the count and it solved. You can see it solves pretty quick. All of them solve in under a millisecond. Did I get rid of it? Yeah, I got rid of that. Okay. Yeah, so not bad. Again, like the first 7 minutes was implementing it, and then just implementing the actual lock thing, and that's where I was like, oh, should I use like a VecDeck or an iterator? That's what took me the time there. But actually, I mean, to be honest, it wasn't that hard. Again, because this is me reading too, so this one took a little bit longer because I had to think about the ranges. And again, like I said, there was I clearly I had an off by 1 bug, and so I the test input was coming back wrong to begin with, and I also had missed the backwards thing, so I had to implement the backwards thing. When I first solved it, it was like I was solving it as if you were inserting the numbers on the left hand side the opposite way. So I had to recognize that difference. And I think what I noticed was where's the example? Oh, I noticed, right? I printed out my array for this test case, and I noticed these numbers were off, and I was like, oh, I've done this side wrong. That's the reason. Okay, good to know. So I think those were the two things that it took me a few minutes to figure that part out. But otherwise, I think then my times were okay, at least in that respect. And then again, once you've solved it for part 2 and you've done the range way, it only took me a minute to be like, oh, it hasn't changed. So get the new input, change the number, run it again. And I think you can see, like, I've set it up like over here on this side to like, I've changed it a little bit. The bottom status bar has like, I keep a running status of like what's happening with my solves and my tests. And then this is like my debug window now, where I can use it to like print information if I need to and stuff like that. So anyway, yeah, today wasn't that bad. I don't want to like jinx it, but it felt good. The last couple days were pretty easy to solve, I think. So okay, let's look at some solutions. Yeah, we already got several comments. I waffled for a while on what data structure to represent the dial wheel with. Ended up with an interval bool tuples, where the interval itself was 2 tuple ranges and the bool represented the range values in ascending or descending. Okay, yep, that's exactly what I did. Same thing too, right? To find the slot, you just modulate the target slot by the total sum. Yeah, perfect. Simple one today, 12 microseconds. Okay, does this dude just have a faster computer than me? Because I don't presume you can do it much more efficiently. Of course, I may be doing other things more inefficiently. Part 1. Unwrap lines map. Take the numbers. Okay, you create a vec to start. Okay. these things probably add efficiency too, is like if you know how big your vector is going to be, you can like pre-allocate it. But yeah, it looks like they're doing something similar, right? Is like if it's divisible by 2. Clippy warns me when I do something like this. There's like a new function like divisible by, I think. That it tells me, hey, why don't you use divisible by instead of that? So if you're using Rust, maybe Clippy might warn you of that too. Not everyone likes to use Clippy. I'm fine with that. Yeah, so if you're putting it on the front, you put it here. Putting on the back, it's there -1, or it's from the lane minus that value. Gotcha. Okay, very cool. Yeah, this is probably inserting it more efficiently than I did, and that's why the time is pretty quick. Rangefinder. Okay, so here's his or their function rangefinder. This is like the solver. So input lines map split once dash left and right. So yeah, you have a start and end in the range. It looks like they're doing the same thing. Okay, but on the fronts, or on the going clockwise, they're putting start end, and counterclockwise they're putting in start. And so that might be also another way that you could store like the whether you're going backwards is just reversing those values, I presume. Left reverse, right extend, left. Very good. Okay, so yeah, this is another way to do it, is you have like 2 vectors, then you're like putting values in those 2 vectors, and then you just extend one with the other. Yeah, that's a cool idea. Okay. Sum. Start end. So you get a sum of all of the values, like all of the ranges. Target equals index modulo sum. Oh, this is an interesting efficiency. So, okay, so what are they doing is they know how big it is. So the real question is like how far. So what I did was I go around the dial a bunch of times, right? If you look at mine, my spin the wheel, I loop and I go around the dial that many times. Obviously I'm jumping back and forward, but I'm going around the dial that many times. In this case, they're saying, hey, I'm going to update my target value to be what I need to get to be the value modulo the sum. So I'm never going to extend past the entire dial, right? I'm just going to go to the point where I would fall, which allows them to, right, go from start to end, do the same thing, and eventually get there. So I might try that. Let's try that really, because I think that will actually make it substantially more efficient, depending on the size of the numbers, right? So we say let sum equal wheel.iter.map lr r minus l dot sum size. And then we say let ticks equal ticks. I guess I can just do ticks modulo. It's going to be +1, huh? And that already speeds it up, right? Just by doing that, because I've like simplified my thing. I guess because I'm only using the total once, I could put it right here. Yeah, that's a lot faster already. That's a cool optimization that I hadn't thought of. So the idea is there's no reason to like keep there's no reason to spin a bunch of times. You already know you're going to do how many full spins you're going to do, and so you can just eliminate those. Or I guess what you can calculate how many full spins you can do and then optimize them. So that's a cool optimization. So now I can also change my for loop because I can say for LR backwards in range or in range. Wheel. Sometimes you get languages mixed up. Anybody else, huh? Anybody? Okay, there you go. Yeah, I like that. That's very cool. Very good optimization. Yeah, that's probably something to think about. Anytime you're doing a modulo operation in one part of the problem, you ought to just be asking yourself, where else can I do modulo operations? Very good, very good. Okay, that's a cool optimization. I like that. Oh, and I think it brings me, yeah, so like 16 microseconds, and their solution is in 12. So that brings me in line like with their solution. So very cool. But again, it looks like I think the solution was similar. What else? Oh, you just kind of figure out whether you're reversed by start versus end, right? So you can compare the start and the end to determine if you're going this way or that way. Okay, yeah, otherwise it looks pretty similar. Yeah, I had to run a couple tests to get mine to work right, so I presume that's what that was. Very good. Didn't go for the most optimized. Let's see what their didn't go for the most optimized was. I mean, part 1 should be easy, right? Okay, this is like this is a very Python-y way of doing the same thing that I did, right? Is like pull every other one and then pull the reverse. So these are like, what do they call them? Or this part right here are like get to the end and skip -2 to 0. It's the equivalent of what I did, I think. Rotate by, oh, that's the number, the constant rotate by line over numbers. Okay, yeah, very similar solution, but in Pythonese. Left nums, right nums. I guess they're probably the same things, right? Okay, we use NumPy though now. Probably because you can do NumPy stuff. Yeah, ranges from string. I'm not totally, I've used NumPy a little bit because I've taken like machine learning classes and some AI classes. I've never used this from string before though. I presume it's like, oh yeah, it is. It's creating a NumPy array, right? And it's saying the separator is a dash and the type is an int. So it's like, this is like doing the splitting for you. It's my equivalent of, although NumPy obviously would work on like, you could give it a whole matrix, presumably, right? It's doing the same thing that I did, where I did the split once by dash and then convert the two sides to ints. And then, yeah, they're adding them to the right side or to the left side and then switching that. Okay. Interesting. So it's actually adding the numbers. NumPy must be able to like do this efficiently with like ranges. I actually don't know enough about Python, so if there's a Python expert out there listening, I'd love to know internally what NumPy is doing with these ranges. Like, is it basically doing what I did in Rust, or is it like creating a whole bunch of numbers? I suspect it's maybe like handling the stuff for you. So that's really cool if you can like leverage NumPy to like solve it for you. That's very cool. It almost makes me wonder if there's like an equivalent in Rust. I'm sure there is. So someone will tell me, I'm sure. Should have waited before. It's quite possible. Yeah, I'll ask them and see what they say. I mean, clearly they know stuff about it. A miner optimized first computes the total sum of the ranges when we take the number of turns modulo the total so that we only need a single pass. Okay, yeah, it looks like this person did the same thing as before, as the other previous solution. It was something like I totally missed. Okay, they also did an iter solution, which I think is cool. You get the numbers, you start with this one, and then you extend it this way, skip this way, reverse. So I did a similar thing. They did it in fewer lines. At the time, I was trying to think it through, but this looks readable enough to me, so that's very cool. Otherwise, it looks like, yeah, I think a lot of people probably solved it this way, right? It looks like they also did it. No, wait. 0, 1, 1 minus 0 plus 1. Oh, is this the, this is the, so on, when you're putting it on the, I guess on the right hand side, I guess, have I been saying those the wrong way? You do 0 and 1, and then you do 1 and 0 on the other side, but they're maintaining a sum here of the size. Okay, and then they use it here for the total. Yeah, so they use that size to get the totals. First, second size in wheel. Remaining greater than equal size. Oh, this is a cool optimization because it's like, if you already have the size, you don't have to calculate it in the thing. I don't know how much time that saves or if it saves you nothing. Usually addition and subtraction's pretty fast, but. And then they do, so I used a Boolean, but it looks like a lot of people are just saying, oh, just compare the two values, and then that'll tell you whether you need to add or subtract. Okay. Yeah, I can see that being, I mean, memory-wise is probably more efficient because this is probably relatively, this is easy to calculate as like getting a bool and stuff like that, right? So it's unfortunate that part 3 can be brute force with the same code as part 2. My wheel has about 275 million of the numbers, and my code runs in 4.5 seconds. Okay. So you could have just taken the part 2 and done it. Okay. I don't know. Maybe you could have done it faster if you knew that way. Took 12 seconds. Okay, they are extending ranges. Okay, so I was wrong. My inclination at the beginning, and I guess it bore out by saying we could do it in 1 gig, but you can basically, it sounds like if you're going for speed, doing this in 12 seconds might be faster than figuring out the more optimal solution. And so, you'd solve this in 12 seconds and get to it. So I still think that's cool. Let's see. We'll reply to him. Very cool. Missed the optimization of doing. And what was his solution? Okay. Wait, did that not submit? Oh no, it did. How do I do this stuff in Okay, we'll leave it as is. Anyway, it was a fun day. I thought it was a cool day, not too hard. Again, I'd done the combination lock a while ago, and so it was I kind of knew what we needed to do. It was just a matter of figuring out how to like put the lock on there and then spin it around. With the one gotcha of like doing the ranges, I think that came pretty okay for me. It wasn't too bad. It did take me a few minutes to implement, but it wasn't too bad. So fun day. I'd love to see your solutions. Post them on Reddit. Send me comments so I can and I'll check your solutions, right? And reply, talk to you, see what and see if we can't optimize it even further. This one I feel is pretty efficient, but I'm sure I think this was a cool optimization that I had missed, but not sure you could optimize it much more other than pre-allocating the wheel sizes. Oh, interesting. I don't know if this will be faster or not, but now that I think about it, you could, for part 1 at least, you don't even have to rearrange the numbers. You could probably calculate which number you're on, whether you're going left or right. You may just be able to do it with math. So that might be a fun thing to try, is like, could you just do it with math, right? Anyway, fun. Lots for me at least. Hopefully you had fun too. And otherwise, I think we'll talk to you next time. Thanks, everybody. Bye.